Okay, thank you very much for the invitation, and sorry for not being there with you live. So I'm going to talk about some work led by Andrew Ross on benchmarking machine learning parametrizations, mostly focusing on the ocean. So really the grand challenge that we're going after here is the fact that we're trying to simulate a climate system, but we don't have infinite computing power. So we're limited in terms of the grid box size that we can use to numerically solve the climate system. So anything that is happening below the grid box size of a climate model, and so for the atmosphere, that would mean clouds, turbulence, radiation. For the ocean, same thing, vertical mixing, isopycnal mixing, mesoscale eddies. All those processes are too small to be resolved by the grid box size of climate model. So what do we do? Well, for decades, the idea has been trying to come up with a simple idealized representation of those processes and their effect on the large scale flow. So usually people come up with a simple mathematical representation that will mimic the effect of, say, clouds on temperature, or mesoscale eddies on different properties in the ocean. Now, of course, they've been really helpful. They've helped improve climate models, but they continue to remain a big source of uncertainty. So the question is, can we actually use data and machine learning algorithm to come up with new parametrizations or new closures of, that will represent actually the effect of those small scale onto the large scale flow. So it's been going on for quite some time. Actually started in the atmosphere with radiation, but really kind of has exploded in the last few years. And so most of my work has been kind of focusing on the ocean, and we've been going at it for quite a few years now. But really the idea was, is there some way to extract information, from the data with machine learning algorithm that will improve the current generation of parameterization? But the problem is every time we came up with, a different data set and a different method. So we wanted to take a step back and really try to come up with a simple, test bed where we can actually develop new methods, but also come up with new metrics and things like this that properly will actually assess how well we're doing, rather than being superficial. Let's put it this way in our testing. So we're going to take the simplest possible model that one can come up with when we talked about mesoscale turbulence in the ocean, and it's really the one where everybody develops and tests their parameterization. It's called a quasi-geostrophic model. And really, we're not after learning a new parameterization per se, but mostly focusing on quantifying how well we do and developing new methodologies. Okay, so what we're going to do is we're going to take those idealized simulation. We're going to learn the missing forcing, so the missing turbulence forcing that the coarse resolution model will be missing, again, by taking data from this high resolution model. So again, rather than us dictating what the missing forcing is, we're going to let a neural network, in this case, a convolutional neural network, learn the missing physics that we'll need to put into a low resolution model to make it behave like a high resolution model as here. Okay, so we're going to take a high resolution run. We're going to extract the subgrid forcing that will be missing from the coarse resolution model. We're going to learn that subgrid forcing with a neural network, and then we're going to take it, put it in a coarse resolution simulation, and hope that the physics of this new simulation will actually be the same as a high resolution one without a computational cost. Okay, but what's critical for us is to not eyeball the results. And so, some of the quantities that we care about in this problem is the energy flux. So here's the kinetic energy as a function of wave number. And what the eddies are supposed to do is to take energy from the small scale. So that's why you see this kind of negative lobe, and put it in the large scale. That's where you see the positive lobe. The coarse resolution run is actually the gray line, and the high resolution is the black one. And you can see the high resolution is doing more backscatter, more inverse energy cascade by taking the energy from the small scale, putting it at a large scale. And so what we're going to do is we're going to quantify the amount by actually calculating the difference between those two curves. So we're going to come up with a score that directly measure that difference rather than just eyeballing it, because we're going to run more than 100 simulation with different parameterization captured from the data. So we really want to figure out a good way and a good metrics to actually test a large number of parameterizations. So the second thing that we're interested in is also the probability distribution function of the large scale variables, right? We want the tails right. We want the standard deviation to be right. So again, we're going to measure the distance between different distribution when we run all those things. Second thing that is actually quite important is the way you extract the subgrid forcing. There are some choices. Some of those choices mean that you need to basically filter and coarse grain the data, and the way you do it is not uniquely defined. So we're going to test that, and we're going to see that actually it's an order one effect on the scale of the parametrizations when we plug them into a coarse resolution. And the third thing, and that's a very important one, is we always have to test against the best physics parametrizations that are out there. Otherwise, then it's a little bit cheating, I would say. And also try to come up with scenarios that are harder to get. And so what we're going to do is we're going to test against a backscatter parametrization, that is physics-based parametrization. And we're also going to test it in a simulation that we haven't learned from, that has slightly different physics. In this case, the physics is jets. And we're not learning on a configuration that has jets. Okay, so here's one result, and it's a bit of an overwhelming plot, so I kind of try to tame it. So what we've done is we plotted the score of basically a similarity score on how well we do for the spectral fluxes versus how well we do for the distribution. So what does that mean? That means that when we're close to 1, so when we're over here, we're doing very well. When we're down here, we're doing very poorly. And here, basically, we have 140 different coarse resolution run with a machine learned parametrization. And those clouds that you see, red, green, and purple, are basically 3 different ways to extract the subgrid forcing. So just by a different method of extracting the subgrid forcing, you already get completely different results without even, tuning hyperparameters of your neural network or whatever, or any fancy things that people like to talk about. Here, basically the data is at the core of the spread. So what you do with your data to begin with is super important. Second thing that is extremely important is make sure that you have real quantitative metrics, right? Because if you eyeball things, then a lot of the results might actually look very similar. But here, by actually coming up with quantitative metrics, we can actually directly understand the similarities and differences between different runs without just eyeballing it. All right, so that's pretty important. So I think that's one of the main lessons here. When we benchmark something, we have to really test the sensitivity across a range. Now, the problem is in some cases, right? So if I go back here, over here, we're doing extremely well with some of the neural nets, but I have absolutely no clue why. So for our next step, so testing against the best available methods and also testing in different scenarios, what we're going to do is we're going to take the best neural network, right? The best coarse resolution model with a neural network. And we're going to compare it to a coarse resolution model that includes a physics-based parametrization, so the negative viscosity. That's like the kind of the best that exists out there. And we're also going to test it against a new machine learning parametrization that we learned from the same data, but using a hybrid method that we developed. So it's a combination of genetic programming and sparse regression. We're going to extract an equation directly from the data. So now it's going to be very sparse. I only have a few coefficients. And we're going to test those 3 methods: neural network, a physics-based parametrization, and a hybrid parametrization. So here we go. So this is the high resolution run, low resolution plus a physics-based parametrization, low resolution plus a neural network, low resolution plus the symbolic expression that we came up with. All 3 do well. If we compare the amount of kinetic energy that they reproduce compared to the coarse resolution, they reach the same level as the high resolution. So they all do pretty well. They improve the distributions as well of the large scale variables. Some do better than others, right? So the neural network, for example, does better. Now the real test is, let's take those 3 parameterization, right? So, and the data-driven one, they were learned on this kind of eddy configuration, and test them in a jet configuration without retraining, without relearning. So this is kind of a step up in trying to reproduce what's right. And again, we're going to compare against the best that are out there, which is this kind of physics-based parameterization. And so here are the results. The physics-based almost does nothing, basically, compared to the coarse resolution run itself. Deep learning does extremely poorly. Actually, it tries to reproduce something that has nothing to do with the truth. And the hybrid symbolic parameterization actually does the best. It starts looking a lot more like the high resolution run. And if we look at quantitative metrics, we also improve quite drastically. So at the end of the day, this kind of sparse representation learned from data is actually better than a neural network that has 1 million parameters, simply because the neural network is overfitting over some of the regimes that it learned. And so there's nothing new here. But really kind of the power here is that with only a few parameters, we were able to extract an equation, right, from data that has only a few parameters in there, and that can actually, improve simulation over a wide range of regimes. So let me give you some concluding thoughts. So first of all, it's very important to find a balance between skill and interpretability. And so I hinted at it at the end, right? Is that physics-based parameterization, you only have one, parameter. It's easy to interpret, but it's quite hard to actually make it work all the time. And it's been a source of uncertainty. Deep learning is amazing. You can do great stuff, but it's, again, hard to interpret and how to be robust. Kind of like this one in between, sparse models, they're very robust, and I can also learn something from the term that we extract, and I'm happy to talk to people if they're interested in it. I think it's very important to actually test extensively your results, so don't be fooled by one good outcome, right? So I showed you this kind of very crazy plot here. So depending on the input and the output that you're using, you can have very different results in your simulations when it comes to parameterization. So machine learning are great, but they're also super sensitive to the data. It's a data-driven problem. So before doing hyper-tuning parameter, make sure that you actually understand how you're dealing with your data, and test it extensively, really as much as possible. Then the last point is, of course, be creative and have fun, because there's a lot of work to be done at the interface between data, machine learning, and climate. But we also need to remember that it's important to do things in a very thorough way. So if you are interested in some resources, we have a preprint out there. There are some GitHub repos where you can actually use all those kind of quantitative metrics ideas, and our new algorithm that is a combination between genetic programming and sparse regression that you can try out on some of your problem if you're interested. Thank you very much.